Hi students, welcome again to the acidic environment, and this particular video is going to focus on volumetric analysis. Now you guys have been spending a lot of time on volumetric analysis over the last week or so, so you already know a fair bit about this, but I thought we needed to put a couple of videos together to just explain some of the techniques a little bit more thoroughly, to identify some of the pitfalls when you're coming to do your practical task, and just some things to, I guess, watch out for. We'll also, in subsequent videos, have a look at some of the calculations involved in volumetric analysis. But at the moment, I really just want to introduce some of the key terms. So the first one is that the particular type of technique that we're using for our volumetric analysis is this technique of titration. And volumetric analysis is a very important technique in chemistry because it's one of the ways that we use to identify the concentration of unknown solutions. So the key to titration is about calculating the concentration of an unknown solution. So one example might be that we know that vinegar contains the acid acetic acid, and so we know that there's an acid present in vinegar, but what is its concentration? We don't know. So we can use the technique of titration to identify what the concentration of the acetic acid is in vinegar. Effectively, when we're looking at titration, what we're looking at is the process by which one reagent, which is dissolved in a solvent. Okay, for our purposes, the solvent would be water. Okay, is added to a second reagent, and this one is also in a solvent, and again, most likely to the H2O from a burette. Okay, this is a specialized piece of equipment, and this occurs until an end point. Until an end point is reached. So we want an endpoint. We want to find some way of knowing when this reaction has reached its conclusion. We want to try and make sure that we have sufficient reagent B to react with reagent A to ensure that we have a complete reaction without having an excess, preferably of either, although in practice that's very, very difficult to do. Now, there's 4 types of acid-base reactions that we can carry out when we're looking at the technique of titration. Each of these reactions is going to need to proceed to completion. We have to have the whole, whatever we start with. So if we're starting with the acid, saying we're titrating against a base, we need to make sure that all of the acid has been reacted, that the reaction has gone to completion. Otherwise, the calculations that we perform in association with our titration will not be correct. So there are 4 types, basically, of different types of reactions that we can have a look at. And if we sort of very broadly plot, and this is going to be very crude, so let's see how we go. So over time, so this is going to be the addition. Let's say this is the addition of the base. Okay, so this is going to be the number of mils of base that we're going to add. And what we might plot here on the y-axis is the pH. So it's starting down at the low mark to coming up to the middle, which is going to be 7, and maybe up to the top, which is going to be something like 12, 14, whatever. So if the first one we're looking at is a strong acid and a strong base, then the strong acid is going to start down here in this range. Okay, the graph is basically going to wander up a little bit, reasonably straight, and then it's going to reach a point where it goes straight up. Okay, it's probably going to come out around about 10 is going to be this point here, pH of around about 10. Okay, and it's going to pass right through this point at 7. And so we're going to need to make sure that we select an indicator that's going to show us this particular point, because it's not going to stop once it reaches perfect equivalence. Okay, it's going to sort of shoot past that a little bit. Okay, I've drawn this kind of squiggly, but it's really very much straighter than that. It's vertical, so it just goes straight up. So the problem that we have is that it's easy to overshoot this reaction a little bit, and that's why you need we use phenolphthalein for this one. Phenolphthalein will be the indicator that we choose, because down in this region it will be colorless, and up here it's this sort of magenta pink, which some of you have seen in full color. And of course what we're trying to do is get a very pale pink color where you've got to put it on a piece of paper to actually see whether or not the color is there or not. And if you've got to keep checking it on a piece of paper, you're doing it right. What happens though if we have, and I'll just change colors for a second so you can see this. All right, so what happens if we have a weak acid and a strong base? Okay, well the weak acid first of all is not going to start down in this region. Okay, it's going to start up in this region. All right, so it's going to again wander through because at this point in time you've got an equilibrium shift. As it's reacting, we are forming more and more of the ions in solution. Those ions are going to be reacting with our hydroxide ions, and so we're going to get a little bit of an upward curve down the bottom here as we use up all of those ions. Then we're going to come to the point, and I'm going to assume that we've still got a kind of a 1-to-1 ratio happening here. The pH is going to come much sort of closer. It's still going to be vertical, and it's still going to come out roughly around the same line. Because we have a strong base in both situations, this region up here is going to be very similar. Okay, but the section at the bottom is going to be different. So once again, we can still use phenolphthalein as our indicator, and that's because we still are going to have an equivalence point that's going to shoot through that place where the phenolphthalein changes color. So speaking of changing color, I'll do it once more. When we go to a strong acid and a weak base, our strong acid is going to come back down here. So it's going to follow basically the same mark to here. But once it gets up to there, then we have a change, because it's not going to come out where it did before. It's actually going to come out a little earlier. Okay. The weak base is going to have a strong conjugate, and that's going to push the pH down a little bit, which means it's going to sneak out down here. That is going to be, it may not look like it here, but it's actually going to be below the point where phenolphthalein changes color. So phenolphthalein is now not a good choice for a weak base. If you have a strong base, then phenolphthalein works perfectly. Okay, both of these two work if the base is strong, but when the base is weak, we need to pick something else. So we need to pick something like methyl orange, or maybe even bromophenol blue, or something like that, because that's going to give us a much better way of identifying exactly where that endpoint is. Now, the fourth one I'm not really going to talk about very much because it's kind of pointless, and it's the weak acid and weak base. And as you probably have guessed, it's going to be tracking basically where the green is here and where the orange is here. So this is a really difficult kind of a thing. The reaction is very slow. It's much more difficult to select any sort of indicator to work with this, so we just don't deal with this. If we're going to need to do this sort of thing, we tend to use something that we call back titrations, but that's a little bit complex for us now. So effectively, there's three types that you will get. The the first one is strong acid and strong base. The second one is a weak acid with a strong base, and the third one is a strong acid with a weak base. For two of these, phenolphthalein is your first choice, and then only if it's a weak base will we use methyl orange. Now, in order to carry out these techniques, one of the most important things we need to look at is a standard solution. Now, I have talked to you guys about this before, but the key to a standard solution is a solution of known concentration. So let me just pop back to the blue color so it can be consistent with these videos. And so it's known. The thing with a standard solution is it must be a known concentration. Now, we can either use a primary standard or we can standardize our solution, that is, carry out the technique of titration in order to calculate what the concentration is. So we can add a known mass of a reagent to a definite volume of solution, and between those, from the mass, we can get the number of moles, and with the volume, we can work out the concentration. The best way, of course, is to select a primary standard, and there's certain characteristics of primary standards or things that make something a primary standard that are important, because not all substances can be fulfill the requirements of a primary standard. And one of the ones that we know is a problem is sodium hydroxide. Sodium hydroxide will absorb moisture from the atmosphere, and so therefore it makes it a poor choice for a primary standard. So for a primary standard, there are a couple of things that we need. We need to make sure that the substance is pure, okay? We need to ensure that it is soluble in water or whatever solvent we choose, but effectively most of the time that's going to be water. We need the reactivity to be with the reagent or with the other reagent. So we can carry out titration reactions that are not necessarily acid and base ones. As long as the two substances will react with each other, then it's going to work. It must be stable. It must have a large molar mass, and then because then any variations in weight will have a very small effect in terms of their percentage or proportion. But also, as with sodium hydroxide, we do not want it no moisture absorbance. Or anything like that, okay? And we also need it to be consistent, okay? We don't know change in mass, okay? So we don't want the substance to be taking on anything else, to be absorbing carbon dioxide from the atmosphere or anything like that. We want it to be consistent. So here's a question from the 2012 HSC, question 4. Which pieces of glassware should be used when preparing a primary standard solution? And you have done this, so which one of these do you think is correct? Well, I'm hoping you selected C. We need a beaker for weighing the mass of our sample, and acid is what we used. We then need a filter funnel, which we're going to use to transfer the solution. Once we've weighed it, we add some water. Then we use the filter funnel to transfer that into the volumetric flask. We're going to use a wash bottle, which isn't glassware, it's plastic, to rinse that, and that will eventually mean we'll have our primary standard in our volumetric flask. Thanks for watching.